Well, here's one of the IB example on optimization. Now, question is Andre wants to get from point A, that is this point, until another point that is here. Now, a straight stretch of the beach is this point, which is along which the Y lies. P is the point on the beach nearest to A. So let's say this is the shortest distance, and PY is 2 kilometers. So he does this by swimming to a straight point Q. So he could have straight away gone swimming to this point, let's say this way, and then travel this distance by walking or running. So what happened is that here we take an optimum route. So he takes some distance by swimming, that is this distance, and then rest of the distance by walking. So our first task is to find out the expression for the time taken for Andre to reach to the point Y. So we get the expression for time first. Like let's have get this distance. So this distance will be x squared plus 4, and this distance that we got here is actually this will be 2 minus x. So net distance travel actually is going to be this. He has to swim this much, and then he has to run this much. So the given condition here is that he covers a 1 kilometer in 5 √5 minutes. Okay, so to cover up this much distance, so if he can swim, let's say 1 kilometer in, so 1 kilometer he covers in 5 √5 minutes, then he's gonna, how much time he's gonna take to cover up root x squared plus 4. So let's say how much time. So if you apply unitary method, this is straight away time taken. If I take t1 is, this is t1. So it is straight away root of 5 √5 plus, I mean 5 √5 plus x squared plus 4. So this is the total time taken along this track. Now, if he takes 5 minutes to complete this distance, 1 kilometer to run, so similarly, it'll be 5 times 2 minus x, total time taken. So this is the expression for time in general, total time taken, that is to come from here to here and then from here to here. So this is our function that was the first part. Now our next objective is to find out the derivative. So dt by dx. Let's do the derivative here. So dt by dx, when we do, we get the 5 √5 as it is, and the derivative of root x squared plus 4 is half x squared plus 4 to the power negative half times 2x plus derivative of this part is negative 5. So now this 2 and 2 get cancelled. So when you simplify this, you get 5 √5x over root x squared plus 4 minus 5. So that's the B part which we get. Now the C part is that dt by dx equals to 0. So equate this to 0 and you solve for x. So we get a 5 √5 x equals to over root x squared plus 4 equals to 5. So this 5 and 5 get cancelled. So root 5x equals to root x squared plus 4, and then you solve for x. So you square both the sides, will be 5x squared actually equals to x squared plus 4. So 4x squared equals to 4. So x squared, this gives us x squared equals to 1. This gives x equals to plus or minus 1. So as you know, the distance can't be negative. So that's why you take x as plus 1. So if I take x as plus 1, it means that person has to actually run square root of 5, swim square root of 5 distance and run 1 kilometer. So this is how you do this. Now we want to see to it that, okay, whether it's minimum or maximum. So let's first find the double derivative. So my single derivative expression is this. So dt by dx we got is 5 root 5x over root x square plus 4 minus 5. So find out the double derivative. Next expression is to find out the double derivative. All right, so this has to be verified basically. So let's do the double derivative. So I apply quotient rule for this part, which is the square v square and vu dash minus uv dash. So it's going to be x square plus 4 as it is, then root x square plus 4 times 5 root 5 minus that's the derivative of this, and minus 5 root 5x times the derivative of x square plus 4, which is root of x square plus 4, which is 1 over 2 root x square plus 4 times 2x. And derivative of minus 5 will be 0 because that's a separate term. Now you got to simplify this. So I take 5 root 5 common, and what I get is root x square plus 4 minus this 2 and 2 get cancelled, minus, and this x times x is actually x square over root x square plus 4 over x square plus 4. Now if I take LCM of this is the double derivative. So 5 root 5, if you take LCM of this times this is x square plus 4 minus x square over x square plus 4 as it is in denominator, which is this, and then times root x square plus 4. So here x, this and this get cancelled, and you get the answer as 20 root 5 over root x square plus 4 times x square plus 4, which is nothing but x square plus 4 to the power 3 by 2. So this is your double derivative. And if you plug x as 1 here now, what we got in the previous part here, so we get the answer is positive. So double derivative is positive, hence it is double derivative is positive, hence it is a minimum. So this is the basic criteria for this kind of questions. Here's another example of the optimization problem. Now, here the question is that the sphere inscribes a cone, and what we have to prove is that with the given dimensions, show that the volume of this sphere, volume of this cone is given by this. Now, first thing is that, like, when I look at the entire height of the cone is actually h from here to here. So this is sometimes a little deceiving when you look at this h. It seems like, okay, h is a radius. So first thing is that the height part of the cone, which is, so volume is 1/3 pi r square times h for a cone. Now the radius of you can see that they don't want the small r, they don't want the radius. So we have to write in terms of capital R and h. So if you look at this part is total h, and out of that this is h minus r. Now if you apply Pythagoras in this tiny triangle here, so this length is h minus this is actually r, this is r, this is h minus r. So what we get is that h minus r the whole square plus small r square equals to capital R square. So you get small r square is actually r square minus h minus r the whole square. Now if you simplify this, you get r square minus h square plus 2hr plus r square minus r square. So this and this get cancelled. So you get 2hr minus h square. So if you plug this r square value out here, what we get is that the volume of the cone is actually 1/3 pi. R square is nothing but 2hr minus h square times h. And if you simplify this, it is pi over 3, which is this, and 2hr, 2h square r minus h cube. That's what we wanted here. Now, given that the inscribed cone has a maximum volume, show that the volume is this. Now you can see that the R is not changing. So let us differentiate this expression with respect to h. So dV by dH is pi over 3 2h square r, which is nothing but 4hr minus 3h square equals to 0. So when you solve equals to for h here, so you get is 4hr equals to 3h square. So h and h gone. So what we get is h is 4r over 3. So height is 4r over 3 we got here. And you plug this height out here. So you get as this will be the volume in that case. So volume will be pi over 3 2r times h is 16r square over 9 minus h cube will be 64 h cube over 27. So if you simplify this and if you take LCM and all, it comes to 32 pi r cube over 81. So that's how you do this particular question on optimization.